Now, for my next two stories will involve exoplanets or planets that are around other stars, sort of keeping this planet or moon like focus. But my first one is about three super Earths that um, are now known to orbit the star HD 7924. And this was a paper that was just published this past month, and the authors are from the University of Hawaii at Manoa, UC Berkeley, the University of California Observatories, as well as the University of Tennessee. So it's a pretty broad collaboration. They used multiple telescopes to observe the system. And this particular star, HD 7924, did have a known planet before. This planet, HD 7924b, or Planet B, but this particular work was able to find these the two additional ones. And they're known as super Earths because they are in this place. They have masses that are significantly larger than the Earth's mass, but they're smaller than Uranus or Neptune. So in our solar system, we don't have any planets that are larger than the Earth but smaller than Uranus and Neptune. But we're finding many examples of solar systems elsewhere where we do find these super Earths. So these are really interesting objects to study because they really don't have an analog here. So they really are a new class of object or a new class of planet. And in this case, these super Earths orbit really close to their parent star. So the star is about 50 light years away, so it's actually relatively close, which makes it a little bit easier to study than some more distant stars. It's a K0 star, which means it's redder and dimmer than our sun. It's about half the luminosity of our sun. And these stars, or these planets, all orbit relatively close to their star. The P here stands for orbital period, so that's how long it takes for this planet to go once around the star, just under a week or 5 days. So it's years, literally 5 days. And these two other planets orbit in 15 days, so just over 2 weeks, and in 24 days. And so they are all relatively close. They're also on the order of about 6 to 8 Earth masses, so definitely much bigger than the Earth. And if you show the orbits, they are all orbiting much closer than Mercury orbits around our sun. So Mercury takes about 88 days to go around, and it's about a third the size of the Earth, but all these are orbiting much closer. And even though the star is dimmer than the sun, because they're so much closer, they receive far more radiation than our Earth does than from the sun. So this innermost planet takes in about 100 times the illumination that our Earth does our Earth gets from our sun, and even the most outermost one, I think, gets on the order of about 24 times as much radiation. And so these are definitely not within the habitable zone of HD 7924. But the telescope that was used to find these additional planets was it's called the Automated Planet Finder, or APF, and this is located at Lick Observatory. Lick Observatory is in Northern California, about 20 miles east of San Jose, and it was actually in danger of being closed down because of budget problems, but it was actually saved recently. But this particular telescope was funded privately, and so private funders spent about $10 million to help build the instrumentation. And they also use observations at other telescopes. So what's really interesting about this telescope is that everything was done um, automatically. This is basically a robotic telescope, and so instead of having people decide what to observe and to be there to make the observations, basically a bunch of graduate students had helped write computer software to automate everything so that the telescope can basically observe 365 days a year if the weather cooperates. So, and this telescope is dedicated entirely to looking for planets around other stars. And so this particular program hopes to find super Earth-like objects, or as many of them as possible, within 100 light years of the Earth. So basically trying to find these supermassive, relative to the Earth, planets that are close enough to be studied in later investigations with other telescopes. And what they did was to use what's known as the Doppler technique, which is the fact that just as we saw earlier with Pluto and Charon, where they orbit a common center of mass or a common center of gravity, the same things happen with planets orbiting stars. And in the cases of these stars, they're orbiting a point that's inside the star, but the star has a slight motion as a result of the tug of the planet's gravity, and you can tease that out and actually determine that a planet is in orbit around it, even though you cannot actually see the planet in your telescope. And so they were able to find those two additional planets, and here is a plot that shows this particular system. So the HD 7924 system with those three planets, and this is a logarithmic plot, so this shows how far they are from their parent star. And Mercury is orbiting about 0.38, so Mercury would be out here. But also plotted on here are 30 other multi-planet systems where the planets orbit really close in. And so we're finding lots of examples of these super Earths, all orbiting close in. And if you find one example of that's kind of an oddball, I mean it could be an oddball, but if you find 30 or 100 or more of these, then you know that there must be solar system formation scenarios where you can have planets like this forming this close to the sun and of this size. And so in this particular paper, they also did some simulations to show that this particular system was actually stable over long periods of time. So it now goes back to the court of the theoretical astronomers to try and figure out how solar systems like this can form so easily, because I'm not sure they were making predictions for systems like this before. All right, so that's my second story, and then for my final story, I want to talk about a news article that came out in the last week or so about a extrasolar planet around the star 55 Cancri that might actually have volcanic activity. And I'll talk about how they were able to discern the fact that a planet that cannot even be resolved or detected directly by a telescope, they can tell that there might be volcanoes on it. So I introduced this idea that planets can orbit really close to their parent star, and the ones that we saw earlier aren't even the record holders. There are some planets like this one, KIC 1255-7548b, which orbits about at about 0.013 astronomical units. So that means it orbits about 1% of the distance between us and the sun. So that's about 25 times closer than the orbit of Mercury to the sun. And it orbits so close that we think that the planet is actually, the surface is boiling off because of the heat from the star, and it's leaving this trail behind like a comet does, a comet that gets close to our sun in the inner solar system. And this is a relatively small object, only about 0.1 Earth mass, so basically like a Mercury-sized object, but because of how quickly the surface is being ablated away, it's thought that this object will basically disappear within a billion years or less. So we have these examples of things that are orbiting really, really close. And so it's thought that you know, there could be other scenarios where the planet doesn't orbit as close, but because it's orbiting so close, the surface is definitely being heated and melted. And so one possible candidate for this is 55 Cancri E, and 55 Cancri is a star in the constellation of Cancer. That's why it's Cancri is in its name. And it's also relatively close, only about 40 light years away. And it's a star that's slightly cooler than our sun. That's what the G8 luminosity class 5 means. And the planet that was previously known has about 8 times the mass of the Earth, so that makes it a super Earth. It's about twice the diameter, and it also orbits pretty close, actually about as close as the other planet, but because it's much bigger, it also has a lot more gravity to hold on to whatever is being melted on its surface. And its orbital period, as you can see, is very fast. It whips around the star in under an Earth day. And given how close it is and what we know to be the luminosity of that star, we think the temperature should be on the order of about 2,000 degrees Kelvin. So that makes it really hot. And people, theoreticians, have actually come up with computer models to simulate how planets forming in systems like this, what sort of materials could end up in their interiors. So we don't really know what the composition of 55 Cancri E is, but according to some of the theoretical models, the interior could be silicate rich, like the mantle of our Earth, with an outer envelope of water, and that water could make up as much as 20% of the mass of the planet. So that's very unusual and very different from anything in our solar system. Or it could be pure silicate with no metals and no water whatsoever. And then there's also this third idea that it's a carbon-rich planet, so that it formed in a solar system where there was more carbon than in our solar system, and you ended up with a planet that's mostly carbon. And what that means is that the carbon towards the center, or even not too far deep in the crust, is under so much pressure that it turns that carbon into diamond. So you have a planet that's made up of mostly diamond. So those are 3 different possibilities. But this new paper that just came out by Demuri, Guillon, Madhusudan, and Kelos, these are astronomers at the University of Cambridge and at the University of Liege in Belgium, use Spitzer Space Telescope observations. So the Spitzer Space Telescope looks in the mid and far infrared, and they acquired about 85 hours worth over a period of about 3 years from 2011 to 2013. And what they did was they observed the planet as it transited, meaning the planet passing in front of the star, and as it was occulted behind the star. When the planet passes behind the star, and the star blocks the planet. And so remember, these systems are so far away that you cannot make out the individual planet. All you're seeing is the combined light from the planet and the star. And whoops. So imagine this is 55 Cancri, and this is 55 Cancri E as it orbits. And this plot here shows the light that we're receiving by the Spitzer Space Telescope as it's monitoring the star. And so as the planet orbits, at some point it passes or transits in front of the star. And so you're seeing the star, but with a bit of the light cut out because the planet is blocking that starlight. And so if you're measuring the starlight, you're going to see a dip in the starlight because you're now seeing the planet's shadow as the planet is transiting. Now, as the planet continues to orbit, what happens is that you see more and more of the surface of the planet lit up by the star. So during this particular phase, when this planet and the star are both visible, in addition to the starlight, you also get a bump in the light because of the reflected light from the planet. So in both these cases, there's a slight increase in the light. And then finally, when the planet is occulted or is blocked by the star, there's again a drop because this reflected light suddenly goes to zero. And now you're only seeing the starlight, so that you have this dip here. And so what they were doing is studying the dip when the planet was going behind the star. And to give you a sense of how difficult these measurements are, 55 Cancri is roughly about the same size as our sun, and 55 Cancri E is twice the size of the Earth, but you can see that it's still a little tiny blot on the surface. And then in comparison, here's how big of a divot the Earth and Jupiter would make in our solar system if they were to pass directly in front of the sun relative to an alien telescope. So you're seeing extremely small changes in the starlight. And since these stars have star spots, they can have lots of variability. You have to make lots and lots of observations in order to confirm that this planet is even there. But it has been confirmed, and they were able to do these additional observations. And what they found was that for 4 occultations in 2012, the amount of drop in the starlight was relatively small. Compared to in 2013, when the amount of drop was about 3.5 times bigger. So what this means is that if you go back to this model, the interpretation is that in 1 year, the planet was much brighter in the infrared than in the other year. And so your interpretation is that the planet at this time in 2012 was only about 1400 degrees Kelvin, and a year later the temperature increased on the surface by more than 1,000 degrees, so up to about almost 2700 degrees Kelvin. And so one possible interpretation is that because the planet is so close to its star, the surface is probably weakened by the heating and the luminosity of that star, and so it's easy for it to be very volcanic or to have lava or magma seas on its surface. And so that explains the actually I think I have these switched around, the temperatures and the years switched around. I apologize for that. So this is actually the 2700 degree Kelvin planet, and this is the 1400 degree Kelvin one, so ignore these labels. They should be flipped. But what the interpretation for why the temperature dropped is that volcanoes erupted and threw out plumes of material out into the atmosphere. And so instead of seeing the surface of the planet, you're now seeing the tops of these volcanic plumes. And these plumes would have to rise maybe 100 to 300 miles above the surface to be cool enough that the temperatures would drop to 1400 degrees. And so that's one possible interpretation. Another might be that there might be material that's actually in orbit around the star, in the same orbit as the planet, and so it just happened that this torus of dusty material was blocking that surface again, but it shows you sort of how if you are very creative, you can get observations where you can come up with interpretations that lead you to amazing results like this. So with that, that's the end of my story, and I'll welcome Dimitri back down to the front, and we will both be available to answer questions.